There was a request for homework problems from homework number 5, so we're going to be doing problems from page 610. We're going to be doing number 42, which was not homework, 43, 45, 63, and 65. Let's start out with problem number 42. 42 wasn't homework, but it's going to serve as an example for what we're supposed to do for these problems. The problem looks like this: 1 over the square root of 11. Now, it's a lot of times considered not fully simplified if you have a square root in the denominator. So we are just going to try and get rid of this square root right here. The easiest way to do that is to multiply by 1, but in a really tricky way. We're going to multiply by 1, but we're going to do it in this form. Square root of 11 divided by square root of 11 is just 1. Anything divided by itself is 1. So we really aren't going to be changing the number. Multiplying by 1 doesn't change the number. But when we do this, what happens is it changes the way the number looks, and that's all we want to do. We want to change the way that this thing looks, not what the actual number is, just the way it looks. If I multiply 1 times the square root of 11, that's just square root of 11. Now on the bottom, I'm going to end up with just regular 11. The reason for this is, I'll explain this two different ways. If I have the square root of 11, and I multiply that by the square root of 11, I could combine those two 11s to be square root of 11 times 11, square root of 121, which is just 11. Now, another way to explain why we're allowed to do this is by actually looking at what the square and square root actually mean. I have square root of 11 times square root of 11. If I have the square root of 11 times square root of 11, another way to write that is the square root of 11 squared. These guys are inverse operations. They're not true inverses, but they act like inverse operations. So squaring kind of undoes this square root right here, and I'm left with whatever is on the inside. So if the square and the square root go away, I'm just left with 11. And that's going to be true for any time I ever square a square root. Whatever's on the inside of the square root originally is going to be what ends up as the simplified expression. Okay, let's actually do one of these problems, and I'll run through as quickly as I can, but I'll try and explain everything. Problem number 43. That's the square root of 5 over the square root of 8x. There are a couple different ways that I could look at this. I could look at this as an entire thing, or I can break this up into the square root of 8 times the square root of x. I could split it apart like I'm used to doing. In this case, I'm not going to. Although I could do it the other way, I'm not going to split it up. It's just going to take an extra step, but there's nothing wrong with doing that. I'm going to multiply by this thing on the bottom. This is called rationalizing the denominator. I multiply this by the square root of 8x. I don't care about what the top is really. All I care about is getting rid of the square root on the bottom. I'm taking the square root of both 8 and the x, so I'm going to be getting rid of both of those aspects at the same time. When I do this, I get the square root of 5 times the square root of 8x over, and square root of 8x times square root of 8x, square root of 8x squared. That gives me just regular old 8x. Again, using that same line of reasoning that I did up here. Same thing will happen if you work it out long ways. Now, I'm not quite done. Usually what happens is if I see two square roots being multiplied together, the simplest thing to do is to combine those two things together into a single square root, and then I take the square root of 40x, the x is supposed to be under the square root as well, don't forget that, and I have that over 8x. And this is as simplified as I can get. This is just another way This guy right here is just another way of writing what I originally had, but in this example I got rid of this. So get rid of the radical in the denominator whenever you can. That was number 43. Next up, let's do number 45. 45 is similar to number 42. We just have a different numerator. So we're just going to run through this one really fast. If I start with 22 over root 11, and then I multiply top and bottom by the denominator, I rationalize this denominator, multiply by root 11 on top and bottom, I'm just multiplying by 1. I get 22 over 11, or sorry, 22 times the square root of 11 over just regular old 11. And when I see something like this, I don't want to leave it, it's not fully simplified yet. These guys both share a common factor of 11. So I can pull out a 2 up here and a 1 down here. So my fully simplified form is going to look like this. 2 times the square root of 11. That over 1 doesn't matter, so I'm not going to include it. This does look a little bit cleaner than this 22 over square root of 11. It's also a little bit simpler to plug into a calculator. 2 times square root of 11 versus 22 divided by square root of 11. Not too much easier, but it's a little bit cleaner. The next one we're going to do is number 63. It's the square root of x squared over the square root of y to the third power. And I'm not going to rationalize this yet. That'll come later on. What I should do is I should simplify it before I rationalize. It's going to make my job a little bit easier. Now, when I take the square root of this guy, square root of x squared is x, and the square root of this guy on the bottom is y times the square root of y, and I could say that that's to the first power. What I'm doing is I'm pulling out a y squared, and then this is equivalent to y squared times y, and when I take the square root of y squared, I'm going to just get y, and then this guy, it stays under that radical. Now I'm not fully finished yet. Let me rewrite this over here. X over y times square root of y. I'm going to multiply the top and bottom by, now I could multiply it by y times the square root of y over y times the square root of y, but I don't really care about this guy because he's not in the radical. I'm only trying to get rid of the radicals, so to that end I'm not going to multiply by y square root of y over y square root of y. I'm going to multiply just by root y over root y. And what happens when I do that is I end up with x times square root of y. I'm just multiplying the numerators together over, I have this y, this circled y, that's along for the ride, and square root of y times the square root of y is just regular old y. So this will give me x root y over y squared. We say that this is simplified, even though it doesn't look a lot simpler than this guy. This guy's a little bit more compact, and it looks a little bit cleaner to me, but when it asks for a simplified expression, always make sure that there are no square roots in the denominator. Number 65. We're going to do this one in two different ways. The second way is going to be a little bit quicker. You should understand both ways of doing it though, so I wouldn't just skip this part. Root 8 times root 10. I'm going to rewrite root 8 as root 4 times 2, and I'm going to rewrite this root 10 as root 2 times 5. Now, this is an exception to what we've been talking about. We've been pulling out perfect squares. This guy is a perfect square. This 2 right here is not a perfect square, but it's going to become clear here in a moment why we're doing this. I'm going to break this one apart, root 4, root 2, and I'll break this one apart also, root 2, root 5. This is going to be a 2. This square root of 4 simplifies to 2. Root 2 times root 2, oh, I know what that's equal to also. That's another 2. So these guys will become 2, and this guy will become a 2. And I'm left with times root 5 here. So this simplifies to 4 times square root of 5. What happens a lot of times is people are able to simplify square root of 8 times square root of 10 to 2 root 2 times root 10, and they go, oh, okay, I'm done. If you combine these guys together though, the square root of 2 times this square root of 10, you get a square root of 20, and this is not fully simplified because you can pull a 4 out of here. So we're actually doing this in a few different ways. So this would be 4 root 5. Now another way to do this is square root of 8 times square root of 10, and then that will give me square root of 80 if I combine these together. Let me do this in 2 steps just so it's clear. I'm doing the square root of 8 times 10. So the quantity 8 times 10, I'm taking the square root of that entire thing, and then I'm going to take the square root of their product, 80. The reason why I might do this method of simplifying, of combining these together first, is so that all the factors end up together. I'll talk about that here in a second, but let's just simplify this. I can pull out a root 16 now, whereas I could not do that before. I could not pull out a root 16. I could not pull out a 4 from that. This is going to be root 16 times 5, and then I end up with root 16, root 5, and this is 4 root 5. Here's the underlying reason why I should combine these. If I have root 8 times root 10, what I actually have is root 2 times 2 times 2. Okay, the fundamental theorem of arithmetic says that there's a unique prime factorization for any number, for any integer, for any natural number. I'm going to pair these guys up. This 2 and this 2 are paired up, and if I combine these guys under one roof, then I can combine this one, this 2, and this 2 over here. And I see that that this guy's left over. I cannot really see it if they're in 2 separate roots, so I should simplify this to root 80 before I even start to get these to simplify this fully.